Hello, welcome again to the lecture series on control systems engineering. In the last session, we were discussing about block diagrams. So we'll continue our discussion, and in this session, let us solve some more examples on block diagram and also learn how to construct block diagram for complex control systems and reduce them to find the overall transfer function. So again, let me consider another example here. We have to reduce this block diagram. You study this, it's a very simple example. So the first point is we'll shift this one from here to here. And then you have to divide this H3 by G4. So we'll get this form. Now this is in canonical form. So this, if I reduce it, I will get this G3 G4 divided by 1 plus G3 G4 H2. Next thing is to get this in canonical form, let us shift this one to here. So then when I shift this, I need to divide by this block, then I will get this one. Then this part is in canonical form. You can reduce this. This will become a single block, it's a feedback block, then you can get this. That I have shown here. Now the whole thing is in canonical form. Now you can apply the formula g of s divided by 1 plus g of s h of s, and you can simplify this and get the overall transfer function. Next, let us consider this example. Here basically what we do is, this is a forward path, this is also a forward path. Take this point, shift from here to here. So you have to multiply by G2. So I have done this. Now let us take this part. These two blocks are in series, we'll multiply and add, we'll get a single block. Fine. Now we can shift this one to outwards. That's what I have done. Now this part is in canonical form, and whatever that block you get, you can multiply with this, you can reduce with this, and finally you can reduce with this one. I think that's what I have done here again. So again, you reduce this part of it, you'll get unity feedback, then complete the solution. Okay, now I have this example. In this example, we can add these two. Okay, then you will get a single block. Multiply with this. Now here we have to split this into two paths. Now let us split this as one path like this, and we'll split this as another path like this. Separate into two paths now. I think that's what I have done here. I have separated this into two parts. So this minus minus will become plus. Then this you can assume it as 1. And these two you can add. And this you can, this in canonical form, you can reduce it. Then multiply, you will get the answer. So same thing here. What you can do is, we can shift this one from here to here first. Then you will get this. Now you can add these two. I've got like this. Next we'll separate this into two paths. One path, sorry, this arrow should be wrong. This is wrong. Like this way it's connected. So this is one path, and this is another path. Okay, I'll separate this into two paths like this. Then this part is in canonical form, then you can multiply and you can simplify. You'll get the answer. Instead of G1, G2 and all that thing, here I have really given the transfer function of each of the components. So this is a real case. So one thing is, we'll shift this one. Then this part is in canonical form. Simplify this, multiply, then again you can reduce with this. Yeah, you will get the transfer function. Okay. So same way, another example, you can just shift from here to here. Then you will get this one. This in canonical form. Then this we can separate into two parts, and we can do that. Okay, right, and simplify, you'll get the answer. It is a much simpler example. Please, you simplify this. So there are something like multiple inputs in a system. R is an input, U is an input. How do we solve such examples? Total output is C. Output C is output due to input R plus output due to input U. Then we'll find out CR separately and CU separately. To find CR, you assume U is equal to 0. To find CU, you assume R is equal to 0. Assume U is equal to 0, then the block diagram will be simplified like this. Then it is in canonical form, you can find CR. To find CU, assume R is equal to 0, then reorganize this in this fashion. And it is in canonical form, find this transfer function. Then you can add CR and CU. In this example, there are three inputs. So we can write C is equal to CR plus CU1 plus CU2. So to find CR, assume U1 and U2 are 0. To find CU1, you assume R and U2 0. To find CU2, you assume R and U1 are 0. And only the case reorganize. Suppose U1 is 0, U2 is 0, then you can simply get the block diagram like this and you can find CR. Same way, R and U2 are 0, then this becomes the forward path and this becomes the feedback path. Okay, you get this. Same way, U2 is equal to R and U1 are 0, then this becomes the forward path and this becomes the feedback path. Right? You will get this. Add all the three outputs. In this case, there are two inputs. There are two outputs. So what we need to do is, first we'll assume C2 is 0. Then this will become two inputs, one output problem. We will solve that. Then you assume C1 equal to 0. Then C2 will be there. There are two inputs. Okay, so which we have solved. So you can just do this exercise. It's very simple, right? Okay, so this is how even complex problems can be solved. Now let me tell you, suppose a physical system is given, how we can form block diagram and reduce it and get the transfer function. I have given a simple electrical circuit here. First, let us write the equations. So for this part of the circuit, the input Vi must be equal to I1 R1 plus voltage drop across C1. Let us call that as V. So you will get first equation. assuming this is V. V equal to 1 by C1 integral of I1 minus I2 dt. So I'll get this equation. Again, this part of the circuit, if you consider, for V is equal to I2 R2 plus V0 we get. V0 is nothing but 1 by C2 integral I2 dt. So we have got these 4 equations. Take the equation number 1. If you take Laplace, Vi of s equal to R1 I of s plus V of s. So I1 of s is equal to Vi of s minus V of s divided by R1. Now you can choose a summing point. Vi of s is a positive value minus V of s negative value multiplied by 1 by R1 must be equal to I1 of s. This is the block diagram equivalent of this equation. Same way, take this equation now. So you will get this after taking Laplace. Now there are two inputs, I1 minus I2. Again take a summing point, I1 minus I2, then divide by 1 by Vs we get. Consider equation number 3 and form the block diagram. So in the fourth equation we'll get this. There are no summing point. Now what we can do is take this I1 of s is the output, then we can connect here. V of s is the output, we can connect here. Then this is I2 of s, I2 of s we can connect to V0 of s. Correct? Then the feedbacks can be connected like this. Okay, now you know the block diagram reduction rule. Shift this one, simplify this. Then after that you shift this one outside, simplify, you will get your answer. Okay, now suppose you have a hydraulic system like this. Okay, now we'll consider this part of the tank. Let us write the equation. Okay, liquid inflow rate minus liquid outflow rate is equal to liquid stored. You will get this. This I have taught you earlier also. From this you will get this equation. Then hydraulic resistance R1, this one is nothing but H1 minus H2 by Q. You get this equation. Okay. Similarly for the second tank, when I write this, I will get this. And R2 is nothing but H2Q0. Now take each one of this equation. Let us take Laplace and form block diagrams. So C1 is H1 of s equal to QA of s minus Q of s. So Qi is input, these two summing point, then 1 by H1 of s will get this. For the second equation, we will get this. Same third equation you can formulate, fourth equation you can formulate. Once you have formulated, then you can pick up those feedback signals and connect them, and you will get the block diagram, and you can reduce this. See, there is no difference between this and the electrical circuit problem I have seen. That's how we can analogously represent using electrical circuits. Right? So this is how we can formulate the block diagrams and reduce them and get the transfer function. Same way you take this armature control DC motor. I have taught you earlier how to write those equations. So EA is equal to LA DIA by DT IARA plus EB. Then EB is equal to KB d theta by dt. T is equal to J d square theta by dt square plus F d theta by dt. T is equal to KIA. These equations. Let us take each one of the equations and take Laplace. Correct. And we'll form the block diagram. So from the second equation, you get this. Third equation, you get this. fourth equation you get this. So now you can organize them and you get the block diagram. Reduce it, you will get a transfer function. These problems must have clearly clarified your doubts how exactly the block diagram concept is useful in finding out the overall transfer function of any complex system. Okay, so you can refer any control system book. There are many examples available and you can practice how to reduce block diagrams. With this, let us end the discussion on block diagrams. Thank you.